Okay. Okay, so to make a start, wait on another minute. Okay, so we've been looking at the project. Okay, so remember last lecture before the study break, we were talking about this big project that you meant to be doing in this half of the unit, and we're meant to design a power supply system. Okay, and to do that, we have some objectives that we meant to achieve. Basically maintain a low impedance for the power supply as seen by the integrated circuits or whatever are needing that power supply to run. Okay, and also the contamination of the generation of noise as well between different circuits, okay, and emissions, okay, as well, okay. And one of the big things that you'll see in the project that we use to control that impedance is these things called power supply decoupling. Okay, so this might be what a power supply looks like. Has a fixed voltage here, perhaps with some noise on it, and that's distributed to a number of different circuits. Okay, and that actual distribution lines will contain some impedance, which will be resistance. Okay, and also some inductance as well. Okay, resistance and inductance. Okay, and when these circuits draw current, okay, they're going to cause voltage drops across those resistances and inductances. So the actual supply you see won't be the nominal supply. Okay, and particularly at high frequencies. So at high frequencies, then things like inductance will become important. Okay, and so one of the ways to mitigate that is to use decoupling capacitors. Okay, so here at the localized circuit, we have some capacitor which acts to maintain this voltage constant, okay, as current is drawn by the actual circuit. Okay, so it tends to smooth out any of the voltage drops that may occur from sudden increases in the current being drawn. Okay, and contains noise to the localized area. We'll talk more about that later. Okay. Also, I think I mentioned earlier that they actually generally supply the power supply lines supply power, but they also provide a common reference for signals. Okay, between circuits. We'll talk more about that later as well. Okay. So in a power supply, we first part of the power supply, we generally have something. We showed that in the pictures before. We have the actual power source. Okay, and that can be something like a linear regulator. Okay, so a linear regulator is generally a circuit that generally looks something like this, where you have a transistor, and this is the unregulated supply, which could be coming somewhere from the AC after going through a transformer and some initial filtering. Okay, and then you have the load here, which is the integrated circuits, etc., and that's drawing a current IL, okay, which is time varying. Okay, and generally what happens is you have some feedback. Okay, so you generally have a very stable reference voltage. Okay, and this output voltage, which is meant to be the supply voltage. Okay, we'll say that's 5 volts, for instance. Okay, that's compared against a particular very stable reference voltage. Okay, and then the particular amplifier compares. Generally, they use something like an op amp. Compares the difference between the output voltage and the reference voltages, and adjusts the current flowing to the transistor. Okay, so this way the actual the feedback mechanism controls the output voltage and makes sure, okay, that enough current is supplied to the load to always make V out to be equal to whatever it's designed to be. Okay, so you have some feedback mechanism, and there's a variable drop between the unregulated supply, which may be varying in time. Okay, and the actual V out. Okay, just to always maintain that V out is always at this 5 volts. Okay, so it turns out there's some exercises on the LMS and also in the reader that if we plot if we look in here and we look at the output impedance looking into the actual regulated supply. Okay, this is 20, and we plot that as a Bode plot. We'd see that at low frequencies, or up to some kilohertz or more, you actually have extremely low impedance because the feedback mechanism is always trying to adjust the amount of current flowing through this transistor such that we always have 5 volts there. Okay, but then at higher frequencies it increases. Okay, the impedance increases, and the reason the impedance increases is because there's a limited bandwidth to this circuit. Okay, so at high frequencies the bandwidth of the op amp used here to and also the transistor used to control the current is limited. Okay, due to RC time constants or whatever. Okay, so the actual current coming out of the transistor can't respond quick enough at high frequencies. Okay, so we see the impedance. Sorry, just turn my phone off. The impedance increase as frequency goes up. Okay, so what component would have an impedance which increases with frequency, conductor, right? So one of the models you'll see in the reader that a model for the linear power supply, linear regulator, is in fact an impedance with an inductance series. Okay, so they actually have, so the noise in this is due to basically electronic noise. Okay, so in resistors you have something called thermal noise, and also in active components like transistors and diodes you have other things called shot noise. Okay, so those are the things that limit the amount of noise or variations that occur on the output of this supply. Okay, on the supply voltage. Okay. We have another type of regulator. So this type of regulator is good for noise, it turns out, but it's not very efficient because you lose a lot of power because the voltage difference between the regulated output and the unregulated supply is always dropped across the transistor. Okay, and you have a certain current IL flowing through that transistor, so it means that power dissipated in that transistor is V drop times IL, right? So there's always power dissipated in those type of supplies. Okay. There's another type of power supply that's often used called a switch mode power supply. Okay, so here to control the actual voltage at the output here, you also have some feedback mechanism. Okay, it's not shown here, but the feedback mechanism basically turns the transistor fully on or fully off. Okay, and so it's basically either the pulse width or the pulse period that's modified. Okay, sorry. Yeah. So here we have some unregulated input. Okay, it's going to produce a DC regulated output. Okay, that's similar to what we had for the linear regulator. Okay, but instead of continuously controlling the transistor with analog signal, it's just basically a binary on-off signal. Okay, so we turn the transistor fully on or fully off. Okay, and that gives some square wave output at this point. Okay, which is then filtered by inductors and capacitors to eventually lead to a DC output. Okay, now the issue with the big advantage of this is that when the transistor is fully on, okay, then it has a low voltage drop across it. Okay, when you saturate the transistor or turn it fully on, it has a low voltage drop across it, and the current's high. But the current's high, but the product of voltage drop times current is low. Okay, when it's fully off, you have very little current. Okay, but you may have a big voltage drop. Again, product of voltage times current is also low, so you don't have a lot of power being dissipated in the transistor. Okay, so these supplies are a lot more efficient. However, on the output here, since this is like a square wave in the unregulated in this region here, you still get some ripple at the output is an issue. Okay, and furthermore, this switching operation of the especially you have inductors here, okay, which are setting up magnetic fields. You're turning them on and off, okay, and that can lead to actual voltage spikes and electromagnetic interference. So generally, these switching mode power supplies, in addition to the fundamental electronic noise in the resistors and the actual active components, also have a lot of extra noise due to the actual switching operation. Okay, so they're generally a lot more efficient, but not as good as linear regulators for noise. Okay, so that's just a bit about power supply regulators. Okay, so I think in this project we'll be looking at a linear regulator. Okay, that's the model you'll be using. Okay, and the other parts of noise in the power supply come from distributing that regulated voltage around the place, and we're going to start talking a bit more about those. Okay, now, so if we look at a typical circuit we might have in for a digital system. Okay, so remember we said that we can model the inputs to a lot of these digital logic gates as capacitance. Okay, and you remember before we had the example of the printed circuit board trace. Okay, short trace with being driven by a logic gate going to another logic gate which is modeled by a capacitance. Okay, so here we have just that. So we have the power supply. The inside of the chip has the transistors, which are connected to the power supply by some impedances, which will probably be some resistance from the wires and also inductance. Okay, and also the output connected to the load via some resistance and induct as well. Okay, and then going to here. Okay, so for instance, we're going from to get this actual input of the firing gate to go from a low to a high voltage. Okay, we'd have to source current from the positive supply in this chip. Okay, and then use it to charge up that capacitance via the short transmission line. Okay, whatever. Okay, and we may also have some capacitance not just between the ground and the input, but also between the input and positive supply as well. Okay, so in this case, we need to have current coming out of positive supply and going back through the ground plane and going with ground, but also it's going to go back into this circuit via the reference plane, okay, which would be the ground, okay. And we could see, for the opposite from high to low, okay, we're actually taking out charge from these capacitors, okay. So and also currents coming from this rail to actually charge up this capacitor, and then we've got current coming out of this capacitor because it's got to be discharged, and again being taken through the transistors in the driving circuit and into the reference plane, okay, to make the final circuit, okay. So we have these transient currents when we do switching in logic, okay. And remember, when we're looking at the example of printed circuit board trace, those switching currents can be really large, okay. If you have fast switching time and you have a finite capacitance, then you need a lot of current, hundreds of milliamps or tens or hundreds of milliamps over a short time to actually discharge or charge these capacitors. So it can be quite significant currents flowing through the system, and the paths that those currents take can be complex and depend on how the load is connected and what the load is, okay. So so some other type of load like a relay, okay. So we may have an example of a power supply connecting up two circuits, circuit A and circuit B, okay. So we have some common impedance from positive supply to circuit A and circuit B, and also some common impedance Z2 from the ground to circuit A and circuit B, okay. So the actual voltage seen, for instance, at circuit B will be this VCC minus this common impedance times IA plus IB, okay. And also on the ground line, it's not going to be precisely 0 volts, right? It will be Z2 times IA plus IB, okay. And so the issues come about when perhaps circuit A draws a lot of current during a transition, okay, and that may cause this voltage here to drop significantly, okay, during that transition, and cause this circuit malfunction, okay. So that's where we get a lot of the issues from having these impedances being too high, okay, or not controlled well enough, okay. So one way we can avoid having those common impedances, okay, is to use something called star wiring. So it's one method of avoiding having common impedances, okay. So in the positive supply, we have for each of the circuits we have a separate line connected back to the power supply, okay. Then hopefully, and if it's well decoupled, okay, then at each of these points and also back here, then when this one draws current, okay, it's not traveling along the same path as the power supply to this circuit, okay. So in some ways that can avoid this situation of having a common impedance between VCC and circuit A and circuit B, okay. But we still have this common impedance for the grounds, okay, and so you can still get noise as the current has to return to the power supply, okay. It's also an issue. And an important thing about the grounds, remember we said that especially in digital systems or a lot of systems, the actual signal that's being transported from one point to another is reference to ground. The information it carries is dependent on the voltage, and the voltage is reference to ground. So if you have noise on the actual ground level, then that may also corrupt the transport of the information that you require, okay. So keep that in mind, okay. So this does help somewhat, but we still have on the ground line, okay. It does not solve signal reference contamination. Okay, so you still have these. Now we could try star wiring a reference as well, okay, but that would probably make the return what would happen on this line even worse, okay, because as current goes through these circuits, you saw how there's a complex path from the power supply through to the load and back through to the ground line, okay. Now you actually have increased impedance between the two, because the path traversed by the current may have to go through Z2 and then back to Z1, okay, complete the circuit, okay? Or there may be increased voltage differences between the ground at this point and the ground at that point, okay, which is what your signal that you're sending from point to point is being referenced to, okay. So there may be increased noise, okay. So one way that can be solved, which we're not going to look at it in this course, is that we use differential signals, okay. So most of the signals we've been talking about so far is where the actual signal is just encoded in one line that travels across a ground plane, which makes a transmission line, okay. And so it's referenced to a particular voltage, okay, ground typically, okay. You could also encode a logic 1 or a logic 0 as being the difference between two signals, okay. So if one signal is more positive than the other, then it's a 1. If that signal is more negative than another, then it's a 0, okay. So it's called differential signaling, okay. So then you're a lot less susceptible to noise in these ground plane, okay, because you're not making a decision on whether it's a 1 or a 0 based on its level with respect at least to the first order, okay, with respect to the ground level. Okay, so you're actually looking at two wires that come across as transmission lines and seeing how they are with respect to each other, and that determines what value the signal carries. Okay, and indeed for very high speed systems like when we have to signal between chips into the gigahertz range, typically how it's done. Okay, it's not done with respect to a ground level, but as a differential signal with positive and negative lines. Okay, and whether it's a 1 or a 0 is represented by which of the two lines is higher or lower than the other. Okay, so that's one way to get around these problems of reference contamination. Okay. So where are we up to? Okay, so we also typically have zones in. We also have zones in the power supply distribution system. Okay, so a printed circuit board power supply distribution system might look like this, where we have our reference and supply signal reference plane. Okay, which might be 0 volts. Okay, and we have perhaps a primary power supply plane which just carries the plus 5 volts, and then we have these zones which supply local supply power locally to various circuits. Okay, and they're connected by some component to primary supply plane. Okay, so down. So this is a diagram of what those sort of systems look like. Okay, so we have power supply, we have one zone has its decoupling, and we have another zone that's decoupling another one as well. Okay, and so that way we can sort of we use that a lot, and you'll use that in the actual project to actually manage the two main reasons we do that is we can make those zones smaller than the whole board size. Okay, and remember, I don't know if you remember, but in the last lecture we talked about the actual printed circuit board has electromagnetic modes, okay, that operate at high frequencies. Okay, and those frequencies at which those electromagnetic modes occur depend on the physical size of the board. Okay, so if you make the board smaller, okay, those resonances of those modes are at high frequencies, which may be away from the region in which you operate in. The other reason is that you can localize noise to different areas. Okay, so perhaps you have one area which is digital, which has a lot of switching, and those fast switching transients typically cause a lot of the noise. Okay, and then in one zone that's contained, and in another zone you might have analog circuits, okay, which don't generate a lot of noise and which are more sensitive to noise. Okay, so that's another reason for doing it. Okay, so I think that's what we talk about here. Okay, and generally, as it says here, there's an issue transmitting information between the zones as well. Okay, if we don't have one rail to be common, remember we talked about that generally the 0 volt rail is considered as a reference, then it makes it difficult to transport signals between zones. So generally, we make that we have one of the supply planes is common, which is typically the 0 volts. Okay, and then we just need to do zoning on the other supply line. Okay, the plus 5 volts or whatever. Okay, and typically with correct design that can work quite well. Okay, so the actual board that you'll be looking at in the project will look something like this. Okay, so you'll have one zone which is a large L-shaped. Okay, and you have another zone which is a smaller zone here. Okay, and then you have these various components that are placed on the board. Okay, and you also have the power supply here. Okay, maybe I'll just show. I do have a printed circuit board here. See what we can look at. Okay, so you can see here, it has lots of integrated circuits on it, here and there and here and there and here, and they're the things that are using the power, and that's why you're making the power supply so that these things run. You also have these other components here. So this happens to be a capacitor. It's quite a large capacitor, both in physical size and in capacitance. Well, I think it's about 10 microfarads. Okay, and that's called a bulk decoupling capacitor. Okay, now. That has large capacitance, but also has fairly large inductance and resistance as well. Okay, so it tends to serve mostly at low frequencies, and we'll talk more about that later. Okay, you also have other sorts of capacitors. You see these on the underside, which are close to the actual. You see the right under some of these integrated circuits, which are a lot smaller and have a lot smaller capacitance, but they have very low inductance and very low resistance as well. So they operate at much higher frequencies. Okay, and we'll talk more about those later too. You also see here that we also have zoning in this particular board. Okay, so we have this main part of which looks a bit similar to what the board that got in the project, because you do have this L-shaped and another little area here. Okay, that actually has something to do with the power supply. So we've done that to basically separate out noise from here to the rest of the board. Okay, I don't know if they've got a ferrite bead on this one. They've got some here, I think. I think these are. It's not exactly the same. It's not the same board as the project, right? This is an actual board that was in production equipment. Okay, it's actually from the 90s, so it's a bit old. But anyway, I think these are ferrite beads here. To be honest, they look like. Okay, could be. Or maybe something else. Okay, so in like 40 years ago, we just had printed circuit boards that just had two layers on them, right? So then you didn't really have proper power planes or proper power supply distribution systems, okay? But then again, generally the actual speed of the devices was very low back then, in megahertz, and the switching times were many hundreds of nanoseconds, right? So you can get away without having complex or well-designed transmission lines and power supply distribution system, okay? Most typically nowadays, printed circuit board will have at least 4 layers, so devote one plane to ground, another plane to VCC. So I think this one has, I don't know what it has, but you can see that these are all the different layers in here. It looks like about 1, 2, can't see, about 6 layers or something like that, at least 6 or 7 layers in this particular printed circuit board, okay? So with more layers, you can do more things, and you can control the impedance of the different transmission lines as well. And if you have very high-speed, complex designs with lots of supply voltages, then you might be many different planes, okay, and lots of ground planes and various signal planes, okay. So it can be really complex, okay. Okay, so the models for different components. So on the in the project, you'll be asked, you'll be designing, you'll use the software to make a printed circuit board and be looking at the impedances at various ports on printed circuit board, and you'll be asked to add in various components to see how it affects the overall impedance of the system. Okay, so some of those models and you use a model for each real component. You actually will be using a model, okay, which is a simplified one, but captures all. Again, models simplified enough, but simplified, but it's complex enough to capture the key characteristics. Okay. Here's a Bode plot of some of the various models, okay, and some of the things we've actually just talked about. Okay, so this magenta line here is the power supply, okay, the linear regulator. Okay, so at low frequencies it has a really low impedance, okay, but at higher frequencies it looks a bit like an inductor, okay, because the bandwidth of feedback mechanism is limited, okay, so it can't respond at high frequency, so the actual impedance goes up. And this green line is the bulk decoupling capacitor I was talking about, the big tantalum one, okay? So it has, initially it's got a fairly low value, because remember that, the capacitance has an inductance of 1 on j omega c, right? Okay, so it should, as frequency goes up, then the impedance should reduce, right? Okay, on a plot. So if we have so an ideal capacitor, that would keep reducing, okay? As you go up in frequency, the inductance would fall off, the impedance would fall off, sorry. But in a real capacitor, you have also inductance associated with the leads that connect the plates together, okay? They'll connect the plate. So if we modelled the capacitor by an ideal capacitor in series with an ideal inductor, and we did the Bode plot for it, then log of Z in, okay, something like that, then we'd see that it'd go down, and it should go down eventually to at the resonance between this capacitor and this inductor, what will the impedance be at resonance? You've got an inductor and capacitor in series, and they're at resonance. What impedance do they give? Anyone? So this is the impedance Z in equals 1 on j omega c plus j omega L. That's going to equal minus j on omega c plus j omega L equals j outside of omega L minus 1 on omega c. So at resonance, okay, which would mean that it would be, what will this term go to? Anyway, 0, right? I'll cancel out. Okay, 0. So this would eventually go to minus infinity, right? This resonance peak would go to minus infinity, right? The impedance, because we're taking the log of 0, right? Anyway, go right down. Okay, but typically in a real capacitor, you've also got inductance, but also you've got some resistance. Okay, and so you'll see that resistance coming in and putting a floor on how far low down you can go, okay, with that impedance. Okay, so the R. Okay, so and that's what you see here with this bulk capacitor, bulk decoupling capacitor. You can see that you have a fairly low impedance at low frequency because it's a large capacitor. Okay, dropping off 20 dB per decade because it's 1 on j omega c. But it should keep going, and then as you come up to high frequency, the inductor takes over. Okay, but around that transition point, what dominates then the minimum impedance that it gets to is this R. Okay, the resistance in the in the actual capacitor itself. Okay, so that's why you have this sort of form. Okay, now the high frequency one, this is the red's the high frequency decoupling capacitor. You can see, okay, at low frequencies, because it's smaller capacitance and the impedance is a lot higher. Okay, but it drops off, keeps dropping off over a much greater frequency range. Okay, and then it will eventually also reach a minimum where it's the resonance and between the inductance and capacitance are at resonance. Okay, and also has some finite resistance. Okay, but it tends to be smaller than for the bulk decoupling capacitor. Okay, and then it starts going up again because it's an inductor. Inductance is a more significant part of the impedance at high frequencies. Okay, and then we have, I think this is meant to be blue here. It's ferrite bridge. So the ferrite bridge they're generally inductors with loss, right? So it just increases with frequency. Okay, I think you get capacitance at high frequency and it'll roll off as well. Okay, so it won't be as ideal as that. Anyway, okay, so we talked about linear regulator. I think there's exercises. It's in the reader. Okay, DC regulator. Okay, lump circuit model. Okay, we have the actual printed circuit board. It's a large structure. We need electromagnetic theory to explain it, but you don't have to worry about that in the actual MATLAB files that you'll be using for the project. That's already taken into account. Okay, and you also see here zoning and all that sort of stuff. Okay, here we are. So in the actual project, as I said, you actually try to model a printed circuit board that looks like this, and you do that by separating this L-type section into two different boards. Okay, but using wires to connect the two boards together, and eventually you'll see that can make quite a good model of what a real L-shaped board would look like. Okay, so the idea, the goal of the project is to try and get the impedance. So this is a log of the impedance seen by various ports into the board. Okay, to get that below some level, say 1 ohm, might be some other level. Okay, over a large frequency range. Okay, and that impedance is made up of a whole stack of different impedances which are in parallel typically. Okay, generally you're going to be placing decoupling components on the board which are going to the ports, which are going to be in parallel with each other through the actual printed circuit board, which has the two planes. Okay, so that impedance, when you add all the components together, is going to be made up of lots of different components interacting. Okay, and having different effects. Okay, so one of those things that you'll see first is the actual printed circuit board itself. So printed circuit board is like these two parallel planes of metal. So what will it look like? It's like a capacitor, right? It's going to look like at low frequencies. It'll look just a bit like a capacitor, okay? Because it's a capacitor's like two parallel planes together, okay? So of metal. So at low frequencies, the power plane looks like a capacitor. So its plot of impedance versus frequency in log scales will be just a straight line going down, okay? And then this B is the output supply voltage from the linear regulator. It's very low at low frequencies, then has this inductor-like behavior at higher frequencies. And then we might have higher frequencies resonances due to the board itself, and then we also have all these interactions between them, which is where things get interesting, which you're going to have to understand to get a good mark in the project. You have to understand why they are occurring, and also put quantitative values to them, okay, and understand what to do to mitigate them. Okay. So just probably at this stage, this is what you're going to get. Might be an idea if I go through, for another 5 minutes, what you're going to get. Okay, so if you go to the project files or project folder, the most important thing you get will be this reader, which I said before you should read. Okay, we've got most of the information you need to do really well on the project is in this reader. Okay, it talks all about the objectives, why you're doing it. All this stuff that you've seen in the slides, and models, for what the various suppliers should be. Okay. Got linear regulator. It's got models for that. Models for different components like an inductor, a power supply, and a harness. Okay, low frequency model. Ferrite bead. So the various models that you can use for modelling different components. Okay. So what else we've got here? The capacitor model.